I'm Evan, and I'm going to tell you about an application of category theory data science involving both monodal categories and knowledge representation. So we all know that computers execute code, but they do so unthinkingly. And a classic problem in artificial intelligence is to try to teach machines to understand code or to understand something about what the code means. And that's an old problem with a long history. In this project, we're trying to solve a specific incarnation of this problem, which is to teach machines to understand the semantics of data analysis tasks. It's in the form of computer code. So at a technical level, the goal of this project is to create an automated method for extracting. Sorry. At a technical level, the goal of this project is to create an automated method for extracting a semantic representation of a data analysis. So a representation that's interpretable by machines. And this representation ought to capture sort of the generic computational aspects of the analysis, such as what operations are involved in the data flow and how they're composed, as well as the concepts that are specific to the domain of data science. So things such as statistical models, data tables, and so forth. And the reason ultimately that we're doing all this is that we want to create an AI assistant for data scientists. And some of the applications that we have in mind are things like automatically summarizing a data analysis in the form of natural language text, or trying to suggest or recommend analyses to people on the basis of what they're doing currently, or even to try to automate certain forms of meta-analysis, or that is known in machine learning, meta-learning. So let me give you an example to show you what I'm talking about. So we have here two toy examples that do a form of clustering called k-means clustering. And it's not so important to know in detail what they do. The point is that both of these toy scripts are written in Python, but using different libraries that exist in that ecosystem. And although they're different programs involving different functions and libraries, they are semantically the same. They do the same thing. And it would be nice to be able to see that in a very transparent way. So, and at least on these examples, our system actually works in the sense that it produces a semantic representation it's the same for both of these analyses. So here's the first one on the left, and on the right we have this data flow graph that those of you who are familiar with category theory will recognize this as a string diagram. So it expresses at least most of this analysis in terms of concepts, universal concepts in data analysis belong to college. Okay, and briefly, here is what is extracted for the second one, and it's the same. So now let me say a very little bit about how we do this. So at the highest level, our process for creating a semantic representation is steps. In the first step, we use techniques from computer program analysis to extract from the execution of the program a data flow graph that we call the raw flow graph. And we call it that because at this level, the nodes and edges of this graph correspond to the actual functions and types that are used in that particular program. They don't have any semantic content beyond what's already present in the text of the program. And in the second stage, which we call semantic enrichment, we're going to try to add that content to the data flow graph to produce what we call the semantic flow graph. And And this stage is what I'm going to focus on for the remainder of this talk, because it's mainly where the applied category theory is happening. And the central object in this part of the process is an ontology about data science. Let me now say something about that ontology. So there are two kinds of things that exist in this ontology. One are concepts, familiar to the general area of knowledge representation. So concepts are supposed to systematize the general ideas that exist in the domain of data. And the concepts are organized into a category, a monodal category. And like any such category, there are two kinds of things in it. There are types or objects, and so these represent the kinds of things that exist in the domain of data analysis, such as models, data tables, and there are also functions or morphisms, and these represent the kinds of things you can do in data analysis, such as reading data from a source of data, fitting a model to data, computing predictions on new data, and so forth. So, and at this stage of the project, we're working with only Cartesian categories. So we're looking at basically the most minimal model you could imagine of deterministic computation. But one of the benefits of the category theoretic perspective is that it's very easy to add additional kinds of structure to model other things in the area. Okay, so in the future, we want to capture more important kinds of programming constructs to model using more sophisticated stuff. Okay. Now, less conventionally, our ontology also has these things which are called annotations. So the purpose of an annotation is to map code that exists in particular libraries onto the universal concepts that are in the ontology. And we think of these concepts as these annotations as all combining together to form a big functor, which goes from some category of concrete code constructs into the concept category that's defining the ontology. And this functor is what's used during a semantic enrichment to go from the raw flow graph. Now, let me just say that this somewhat elegant picture has to confront reality in one unfortunate way, which is that it's very impractical to suppose that you will have an annotation for every type or function that a programmer would use. So, in some sense, this functor has to be partial and then it has to be completed, but that's not something I'm going to go on. So, to give you a sense of what I mean here, let me go back to this first example, this first script that uses the library SciPy. So here's the raw flow graph for this analysis, and these are exactly the functions that are in this script. So this k-means2 function has an annotation which explains how this translates into a whole program in the abstract language of concepts. And if you go back to this, you can see how in the expansion process, this single box will be expanded into a subtype. So that's at a very high level way. So thank you everyone for your attention. I have a few references here in case you're interested, and if there's time, I'll take a question.